After a short stint with the AECL as an NSERC postdoctoral fellow, he started his career as a researcher in private industry with Schlumberger and Dole, moving on to the Nevis Cyclotron Labs, and then a position as senior accelerator physicist at the High Energy Electron Accelerator CBAF in Virginia, before returning to TASC, which was Chalk River's own superconducting cyclotron in the building. For those of you who know the campus at CRL, it's building
137.
137.
114 was Toronto, and 137 was the
Yeah, so just before the main security building 701, there's that huge building that used to have this nice TASC facility. So during his career, he made important contributions to ion source and electron gun development for accelerators, neutron sources for oil and gas exploration, and was the originator of the photovission method for producing radioactive ion beams at TASC at that accelerator facility. So since 1998, he's been a senior researcher in AECL's Fluid System Technology branch, mainly working on robots for can-do radiated fuel handling and in research for the Generation 4 reactor concept. Currently, he's working on the potential use of photoneutrons for medical isotope poly-99 production. So please join me in welcoming Bill to this evening's meeting.
Find the right button for this laser, and I guess I can get started. So, I thought I would like to put together a little different talk tonight, especially since I had the convenience of a captive young audience. That's something one doesn't have very often in my career, so I'm glad to see you all are here tonight. And I'm going to try to present a talk that's I think you'll find a little difference. I call it critical thinking in science. So I think I can go over this quite quickly because we just had all we just covered, but I thought I'd give you a little bit of it. I started here at Chalk River well before all of these were born, except for a few deaths in the audience. Back in January '65, I spent 6 qual terms here as a student and a couple of summer research terms as a master's student. Went on and did my PhD in Toronto between '69 and '74. Back to Chalk River for a few years in '74 and '75, and then my sojourn at 3 different locations in the U.S., and then I came back and have been working here for the last 20 years. And so, as part of that career, there has been a lot of different aspects of science and engineering. I probably worked 20 years in accelerator physics, numerous other things, including the last 12 years, which I call myself a pretend engineer, which is sort of my last descriptor, I guess. So, the sort of basic theme of the talk is critical thinking in science, I'm going to say in general, just in general. But, as I noted here, many of the audience, and I was glad to see that I had made a right guess in that, many of the audience are young and just getting started in their careers in science. And as you go into that career in science, even by now, I'm sure most of you must be aware of somebody writing great claims of how you can solve the energy problem with a bunch of windmills, or how you can, drill a hole 15 kilometers under Toronto. As I picked that little headline, happened to be the day I was writing my abstract, and I said, I need an outrageous abstract. That one looks like a good one. Many other things. There's always somebody looking for, trying to pretend some idea is going to solve a major problem. And undoubtedly, during the careers of most of you young scientists, young potential scientists here, and I hope a lot of you has become scientists that are some sort or other as you go forward. And so you will see a lot of those sort of claims. And as you see them, you should be thinking a little bit, what's the reality of this? Has this really got any chance of happening? So I've said classic examples of this are the present dialogues in climate change and energy. So as you see, I'll be talking, almost all my examples will be on energy. I really haven't spent nearly as much time looking at climate change, but part of my early career was working with Schlumberger, which was a very large company that makes tools that are used on the oil well. So I spent 6 years developing very sophisticated tools that are used at the bottom of 2 and 3 mile deep holes, trying to understand whether there's oil down there. And one learns, as you try to develop those sort of tools, that technologies for using those applications are very difficult. And so it got me interested in oil and the oil patch, and then later on in energy, and then of course, the last number of years working in nuclear energy, so I've had a rather broad personal overlap with energy, and that's where a lot of my interests are, and you'll see this going forward in the talk tonight. So how does one do? How does one approach this? Well, I mean, the very obvious one is it's always the case. If it looks far-fetched, it probably is. Always look at what's being said. Ask yourself, does it make sense? So, in a lot of these areas, and especially in areas of energy, a lot of the big picture questions are actually have a basis in some pretty basic science. You probably have a lot of the science you need already at this young stage of your career to be able to look at some of these questions. And a little caveat to that is all too often people talking about these things tend to ignore the basic facts that are out there. So my encouragement is, as you go forward into your various careers, try to develop a questioning attitude, be able to make reasonable estimates. I mean, a lot of the stuff that we in an older generation have had to do one way or the other, or the calculators, or back of an envelope calculator says code, you can now go and look up in Google or some similar thing. But I still really encourage people to be able to do essentially a back of the envelope, or sit and just put the numbers together in your mind. A lot of these things you can actually do without ever you taking a piece of paper out. And so that's the sort of scale of what I'm going to be talking about for the next while. Now sort of the aspect of it that I would call from correct answers to estimates and guesses. At the levels of high schools and universities and stuff like that, most of you will find that you're graded on things like problems. I mentioned it's still the same as after all the years, that you still have problem sets and other things that you're graded on, and you get rights or wrongs or partial answers or stuff like that. But in general, at the sort of lower level, you'll find that there are correct answers. As the questions start to become a little broader, there's often not a simple right or wrong answer. And I figure that's fine for this summer. Good example. Will we have a nice weekend? Well, based on what we've had, I mean, the definition of everybody in here of what a nice weekend might look like is probably different. So, what your idea of what a nice weekend is probably going to focus what your answer might be to that. So you start already getting into, qualitative answers. There's not necessarily a right or a wrong answer. There's an answer that's based on your particular view of the subject. As you get to the broader topics and climate change and energy, all of a sudden the sort of answers become far more complex, and right and wrong answers become much harder to sort of state, in a hard factual answer. This is correct or this is not correct. So as I tell on here, experience will help you make maybe a better guess, but many experienced people often forget or ignore the basic science. And so, just because you see it from somebody like yourself giving something like that, don't take that it's being correct. You should actually think about it yourself. You should be able to sort of look at what I'm saying and say, this doesn't make any sense. Just because he's, sitting up here giving a lecture, does he actually know what he's talking about? Perfectly reasonable question you should be asking. So what are some of the basic tools? And now I get into some basic, I think, high school or university physics and chemistry. What do I do? For many of these things that I play around with, a few basic ideas in science. Avogadro's number is absolutely fundamental to an awful lot of things that one does in science. The basic, how many particles in a mole of a substance. I pulled this part out of a website and I added a little bit there. For 99% of everything I do, I use 6 times 10 to the 23rd, because one doesn't, for these sort of ways of approaching things, one doesn't need accuracy. One really needs a feel of what it is. And so if you're answering to 20 or 30%, it's a good answer. You don't need to know it to 1% or less. And another equally important one is this, Charles or Boyle's law or something like that. I can't remember my old physics, but basically that 1 mole of an ideal gas has a volume of 22.4 liters at standard temperature and pressure. Again, a very basic, very important part of science. And a couple more useful numbers that I sort of keep these basic numbers in the back of my head. I can sort of know these without, I can sort of immediately pull them out of the air and use them. That's the elementary charge on an electron, a 1.6 10 to the minus 19 coulombs per electron. So that's basically 1 electron volt. Is actually an energy. The energy an electron gains as it travels through the potential of 1 volt. And the one over that number is also a very useful number. That's basically how many electrons per second you get in an ampere. So again, that's the number of charge or quantity of charge flowing. So these are 3 or 4 very basic numbers in science that can be used in an awful lot of different ways in making basic estimates.